Welcome in video 9 on fair valuation, where we will have a look at two exercises, exercise 13 and exercise 14. Exercise 13. We will build up the exercise by adding assets, traded assets to the stock market. So therefore we start with 13.1 and then we will have 13.2 and 13.3. So we consider a financial actuarial world with omega, the universe, the set of all values, the set of all outcomes at the end of the year in which we are interested. And this omega is four couples, consists of four couples, 0, 0, 0, 1, 1, 0, and 1, 1. The first component of each couple denotes a possible price Y1 of stock 1 at time 1. And the second component, the value of the survival index I at time 1. So for instance, the couple 0, 0 is the outcome where the value of the stock will be 0 and the value of the survival index 0. So as you see, both value of the stock and survival index can only take the values 0 and 1. There are some probabilities related to the four couples. P00 is the probability that the stock will go down to value 0 and the index will be equal to value 0. This is 1 over 6. P10 is 2 over 6. P01 is 1 over 6. And P11 is 2 over 6. Now, in this financial actuarial world, there is a traded zero coupon bond, a traded stock, and then there are some other claims which are not traded, but in which we are interested. The zero coupon bond has current price 1 and price at time 1 also 1. So we assume again that the risk-free interest rate over the 1 year period is equal to 0. There is also a stock which is traded at the current price of 1 over 2, and its price at time 1 can be either 0 or 1. The claims that are denoted in red always will be the traded claims. So the other claims that we consider now are non-traded claims. First of all, there is a non-traded survival index, I, which can take the value 0 or 1, whether few people survive in a given population or many people survive. And there is also a non-traded combined claim, and this combined claim looks as follows: 1 minus y1 multiplied by 1 minus I. It is always 0, except if the stock market goes down to 0 and few people survive. So this non-combined claim, again, is only 1 in case of the joint event of a stock market going down and few people surviving. First question that we have to answer: show that the survival index is an orthogonal claim in this setting. Let's take the solutions. So if we have to prove that the index, the survival index, is an orthogonal claim, actually we have to prove that I is independent of all traded assets. There is all traded risky assets. There is only one traded risky asset, namely Y1. So we have to prove that I and Y1 are independent under the measure P. Or we have to prove that the probability that Y1 takes the value Y and I takes the value I is equal to the product of the partial probabilities. And this must hold for all possible outcomes Y and I. Now, we know the probabilities under the measure P. We know the measure P. So we first calculate the marginal probabilities. P0 dot is the probability that the stock has value 0. Is equal to the sum of the probabilities P00 plus P01, or it's equal to the sum of the probabilities of the events leading to a stock value 0. And P01 and P01, P00 and P01 are 1 over 6 and 1 over 6. So P0 dot, the probability that the stock will be equal to value 0, is 1 over 3. In the same way, we can calculate the other marginal probabilities, the probability that the stock equals 1, and then the probabilities of 0 and 1 for the index. And then it is easy to verify that we have that P00, for instance, the probability that we are in the scenario 00 is the product of the probabilities of the marginal probability of the marginal events P0 dot and 0 dot and dot 0. And this holds for any of the possible outcomes. So that means that I and Y1 are indeed P independent. So that means that I is an orthogonal claim. Indeed, as we have to prove. Second question, we have to prove that the mean variance hedge of I of the orthogonal claim is 1/2 0. So that means we buy 1/2 0 coupon bonds and 0 units of the stock. This proof is also easy to make, namely, I is an orthogonal claim. That means that the mean variance hedge of I is an investment in 0 coupon bonds only, and how many 0 coupon bonds do we buy? The best estimate of I. R is now equal to 0, so we have the expectation of Y. And what is the expectation of Y? That's the probability that the index is equal to 1, and this probability is 1/2. So that means that our mean variance hedge of I consists in buying 1/2 0 coupon bonds. Let us have a look at question 3. Now, the question is to determine the mean variance hedge-based value rho I of the survival index. So rho I is, of course, the time 0 price of the mean variance hedge of I, but we know the mean variance hedge of I, plus then pi. Pi is an actuarial valuation or a model consistent valuation, pi of the hedging error of I and the mean variance hedge. Let us have a look at the solution of exercise 3. Well, rho of I is, we repeat here the formula. Now we know that the mean variance hedge of I is 1/2 0. Y, the time 0 vector of the price, the time 0 asset prices, is 1 and 1/2 plus pi of I minus 1/2/0 multiplied by the time 1 vector of asset prices. If we work this out a little bit, we find that rho of I is 1/2 plus pi of I minus 1/2, and the value, of course, depends on the choice of the pi. Now, in question 4, we will now determine the numerical value of rho of I in case pi is the cost of capital principle. So in case of the cost of capital principle, we have that rho of I is the time 0 value of the mean variance hedge of I plus 6%, that's the cost of capital, multiplied by the value at risk at level 99.5 of the hedging error of I when hedged by the mean variance hedge. Let's have a look at the solution. Well, we have to calculate here rho of I is 1/2 plus pi over pi of I minus 1/2, or 1/2 plus 6% of the 99.5 value at risk at level under P of I minus 1/2. So the first thing we want to do is have a look at the distribution of I minus 1/2. I minus 1/2 can take two values, minus 1/2 and plus 1/2, depending on the outcome of I, which can be 0 or 1. Okay. So if we then look at the distribution of I minus 1/2, there is a first possible value at minus 1/2 with probability 1/2, and then there is a second jump at level plus 1/2 of 1/2 here. Now we have to calculate the value at risk at level 99.5%. The 99.5% is here. The value at risk at level 99.5 of this distribution is the maximal value of this distribution, 1/2. So what do we find here? Finally, rho I is 1/2 plus pi of I minus 1/2. We fill in all the things that we have calculated, and we find rho of I is 0.53. That's question 4. So we determined the numerical value rho of I in case pi is the cost of capital principle. Let us continue and go to exercise 5. Let us now look at the claim S. Remember, the claim S was 1 minus y1 multiplied by 1 minus I. We want to determine the mean variance hedge of S, then we will determine the mean variance hedge-based value rho of S for a general pi, and then we will determine the numerical value in case of the cost of capital principle. So it's the same structure as what we did with I. But let us first have a look at the mean variance hedge of S. The mean variance hedge of S, we can calculate it in different ways. Let us have a look at the first way. So S is 1 minus y1 multiplied by 1 minus I, or we can write this as sh multiplied by S orthogonal with sh 1 minus y1. So that's y0 minus y1. Or to write it in as a vector product, it's 1 minus 1, so that's the investment strategy, multiplied by its time 1 value. So the underlying hedging strategy or the mean variance hedge of 1 minus y1 is of course 1 minus 1 minus 1. So you buy 1 zero coupon bond and you sell 1 stock. That's the first part that we already know. The second part, 1 minus I. We know already that I was orthogonal. Then of course also 1 minus I is orthogonal. And the expectation under P of S orthogonal is 1 minus the expectation under P of I is 1 over 2. Now we can calculate the mean variance hedge of S. The mean variance hedge of S is the mean variance hedge of SH multiplied by S orthogonal with SH and S orthogonal defined here. Okay. The mean variance hedge of such a product is the mean variance hedge of the hedgeable part multiplied by the expectation of the orthogonal claim, or that's 1 minus 1 multiplied by 1 over 2 is 1 over 2 minus 1 over 2. So we buy here, the mean variance hedge of S consists of buying 1 over 2 zero coupon bonds and selling 1 over 2 stocks. There is a second way, a more official way, let's say, or following the standard procedure to determine the mean variance hedge. Let's have a look at it. So the mean variance hedge follows from this set of equations. We have seen that the mean variance hedge can always be determined from this set of equations. We have here M equations that determine the theta ms M for that determine the theta ms for the first M values, and then we have the theta 0 for the zero coupon bond. Now, in this particular case, we have only one traded risky asset. So this set of M equations reduces to one equation, and theta 0 looks like this. We have to calculate the covariance of y1 and y1, or the variance of y1, the covariance of y1 and S, and the expectation of S and the expectation of y1. This is all calculated here, 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 and here. Look at it, and then you will find all these values. Okay. Then next, we fill in all these quantities that we have calculated in our set of equations, and we find this set of equations. Or if we work this out, we find that theta mean variance of S is 1 over 2 minus 1 over 2. And that's exactly the same mean variance hedge, of course, as the one that we determined previously. Then we have question 6. Now that we know the mean variance hedge of S, of the combined claim S, we will determine the mean variance hedge based value rho S of S for a general pi, for a general model consistent valuation pi. Let us have a look here. Question 6 is here. Rho S is the mean variance hedge of S multiplied by the time 0 vector of prices plus pi of S minus the mean variance, the time 1 value of the mean variance H of S. We know this mean variance H of S. We know the time 0 vector, and this is the time 1 vector. If we work this out a little bit, this is the rho S that we obtain. 1 over 4 plus pi of S minus 1 over 2 plus 1 over 2 Y1. That is the general expression for question 6. And then we can go to question 7. Now we will look at the special case of question 6 by assuming that pi is the cost of capital principle with the cost of capital of 6%, and where we look at the value at risk at the 99.5 percentile. Let's have a look at the solution of question 7. So we have rho of S is 1 over 4 plus pi of S minus 1 over 2 plus 1 over 2 Y1. We have seen that before. Now, pi of S minus 1 over 2 plus 1 over 2 Y1 is 6% multiplied by the 99 point value at risk of S minus 1 over 2 plus 1 over 2 Y1. So we have to determine the distribution and then the value at risk of this random variable. We rewrite S minus 1 over 2 plus 1 over 2 Y1 a little bit, and it turns out that depending on the situation, on the scenario 0, 0, 0, 1, 1, 0, 1, 1, we have an outcome 1 over 2 minus 1 over 2, 0, 0. If we plot this distribution of S minus 1 over 2 Y1, we get this figure. And now we have to determine the value at risk at level 99.5. 0.995 is somewhere here, so the value at risk will be 1 over 2. So if we fill in all what we know now in our rho of S, we find that rho of S is 0.28. Okay. Now this was exercise 13.1, where there was only the zero coupon bond and the stock traded. Let us now go to exercise 13.2. We have the same financial actuarial world with the same scenarios in which we are interested, with the first component here being the stock and the price of the stock at time 1, and the second component, the value of the survival index at time 1. We have the same survival probabilities, but now, apart from the zero coupon bond and the traded stock, also the survival index is traded. So we extend our market a little bit, so our market will become closer to completeness. The survival index is traded. The current price of it is 2 over 3, and the payoff at time 1 is just I. So at time 1, the claim pays you the outcome of the survival index. And there is also the non-traded combined claim as before. S is 1 minus Y1 multiplied by 1 minus I. Given this extended market, let us now determine the mean variance H of S. The mean variance H of S now consists of 3 components, and we will be able to prove that the mean variance H of S is 2 over 3 minus 1 over 2 minus 1 over 3. So you buy 2 over 3 zero coupon bonds, you sell 1 over 2 stocks, and you sell 1 over 3 units of the index. Let's try to determine the mean variance H. Well, the mean variance H in general is determined from this set of equations with all the covariances included. From that you can determine theta S1 and theta S2, and then the theta S0 follows from this equation. There is a number of quantities that we have to calculate, expectations, covariances. We make all these calculations here, and in the end, we will find that theta mean variance H has to satisfy this set of equations. If we work this out, we indeed find that the mean variance H of S consists of buying 2/3 zero coupon bonds, selling 1 over 2 units of the stock, and selling 1 over 3 units of the survival index. So we answered question 1 now. Question 2 now, let us determine the mean variance H based value rho S of S So the rho S is the time zero price of the mean variance hedge of S plus pi of the hedging error, and pi is a general model consistent valuation. Well, the solution is again easy. Rho S is equal to the mean variance hedge of S, its time zero price, plus pi of the time one value of the hedging error. We know the mean variance hedge of S, that's 2 over 3 minus 1 over 2 minus 1 over 3. We know the time zero vector, that's 1, 1 over 2, 2 over 3. And we know the time one vector, y here is 1, y1, I. If we work this out all together, we find rho of S is 7 over 36 plus pi of S minus 2 over 3 plus 1 over 2 y1 plus 1 over 3 I. Now question 3 is again similar to what we have seen before. We will now determine the numerical value of rho of S for this case, but pi now is the cost of capital principle. The cost of capital principle means again that we take here 6% of the 99.5 value at risk of the hedging error. The solution of question 3 goes in the same line as what we did before. We have to determine first the distribution of S minus 2 over 3 plus 1 over 2 y1 plus 1 over 3 I. And if we plot this distribution function, this is the plot. We have to determine then the 99.5 percentile. So that is again the maximal value 1 over 3. If we fill this in, if we add all these things in our formula, general formula for rho of S, we find that rho of S is 1 over 193 divided by 900. So we answered all the questions in case our index is traded at a given price. But let us now go to an exercise which we will call 13.2 prime, where we assume that the index is traded at a value y2. It must be somewhere between 0 and 1 to exclude arbitrage, but it's a deterministic value somewhere between 0 and 1. We consider the non-traded claim S, and we want to determine the mean variance hedge-based value of S by this principle, just as before. So the exercise is exactly the same as in 13.2, except that instead of the given price, the numerical value, we call it just y2. Then you can show that rho S now is 131 minus 100 y2 divided by 300. So that means it's a decreasing function of the price of the index. So it's clear here that the value of our unhedgeable claim strongly depends on the financial market, in particular on the price here of it's visible here that it's depending on the price of the index, of the traded index. Let us have a look at the solution. Well, we know that rho S is the time zero price of the mean variance hedge plus pi of S minus theta mean variance hedge multiplied by y. Both the mean variance hedge of S and pi of S minus the theta mean variance hedge S multiplied by y do not depend on the time zero vector of prices. So we have here 2/3 minus 1 over 2 minus 1 over 2. And then multiplied by the time zero vector. The time zero vector is 1 over 2. And instead of 2 over 3, we have y2 plus 0.06 multiplied by 1 over 3. If we work this out, we find indeed that rho of S is 131 minus 100 y2 divided by 300. Again, clearly demonstrating that the value that we attach to a claim strongly depends on the financial market information. Let us now go to exercise 13.3, where we will again, we are in the same situation as before, but we will extend our market again a little bit. So we have the universe, the scenarios in which we are interested are still the same as before. There is the price, the first component is the price of the stock, the second component is the value of the survival index. These are our probabilities, but now we assume that apart from the zero coupon bonds, the stock and the survival index, also there is a call option traded, and this call option has current price 1/6, but payoff at time and payoff at time 1 is equal to I times Y1 minus 0.5 plus. So what does that mean? The payoff depends on survival and also on survival in the population and of the financial market information or the financial market evolution. There is again the non-traded combined claim, and we have to value now this non-traded combined claim. You can imagine already what is the first question. The first question will be, show that the mean variance hedge of S is given by 1, minus 1, minus 1, 2. So now the mean variance hedge consists of 4 components because there are 4 traded assets in the market, including the exotic option that we just defined. Well, question 1 is solved as follows. We know that S is by definition 1 minus Y1 multiplied by 1 minus I, or it is 1 minus Y1 minus I plus I times Y1. I times Y1 can be equal to 1 or 0. It's 1 in the scenario 1, 1 and 0 otherwise. Let us now have a look at the payoff of the new option that we introduced. I minus Y1 minus 0.5 plus is only equal to 1/2 if we are in the situation 1, 1 and is 0 otherwise. So that means that Y1 multiplied by I, which was defined here, is equal to 2 times Y, the time 1 value of the exotic option. Or in simpler notation, Y1 multiplied by I is 2 times Y3. Hence, we have seen here an expression for S. This expression for S can be rewritten as 1 minus Y1 minus Y2 plus 2 times Y3. Or we can write S as the time 1 value of the trading strategy in U, where U is 1 minus 1 minus 1, 2. This 1 minus 1 minus 1, 2 comes, of course, from the components here in this expression. So we find that the mean variance hedge of S is 1 minus 1 minus 1, 2. Now, you can prove, it can be proven that the market here in this exercise, in exercise 13.3, is complete. The market is complete. We will see that further. But given that it is complete, we will not use this completeness for the moment, but this completeness means, in fact, that the mean variance hedge of S, the time 1 value of the mean variance hedge of S, is equal to S. Let us now have a look at the second question. We have to determine the mean variance hedge-based value, rho S of S. In a general case, rho S of is the time 0 price value of the mean variance hedge of S plus pi of the hedging error. The exercise reads as follows, or the solution reads as follows. Rho S is time 0 price of the hedge plus pi of the hedging error, is the mean variance hedge of S multiplied by Y plus pi of 0, because we see here that the times 1 value of the mean variance hedge of S is indeed equal to S. We have seen that somewhere above here. S is 1 minus Y1 minus I plus I multiplied by Y1, or better, we can better show it here. S is equal to nu times Y, so S is hedging. Then we get, if we work this out, we fill it in here, and we work this out, we get rho of S is 1/6. So this was now the second question of exercise 3. Let us now have a look at exercise 14. That's the next exercise. In this exercise 14, we consider a national population of a number of members, and we denote this number by N national. And then for each of these members of the national population, let's say the Belgian population, we attach to each of them a Bernoulli variable, which can take the values 0 or 1, whether the specific member under consideration dies before time 1 or survives. The national survival index, I, is then the sum of all the Bernoulli random variables. So the I denotes the number of survivors, let's say, at the end of the year. Next, let us consider an insured population of what we will denote uninsured members. For each member of the insured population, we also denote an indicator variable, a Bernoulli variable, which is 0 or 1, if the insured I dies before time 1, or if he survives until time N. The insurance benefit payments at time 1 are then given by G1 plus G2 plus Gn insured. So then we count the number of ones in the Bernoulli random variables. Important is that the insured population for this moment doesn't have to be a subset of the national population. So let's say the national population is a Belgian population, the insured population is a population in Italy, let us say. Then we assume that there is a financial market consisting of 3 assets. There is a zero coupon bond, which current price is 1. The risk-free interest rate is R, so the price at time 1 of the zero coupon bond is e to the power R. There is a stock with current price Y1, and price at time 1 is a random variable Y1, a random variable Y1, which takes values in A. And there is the national survival index with current price Y2 and price at time 1, Y2 is I. So the national survival index has a current price Y2 and pays you the number of survivors in the national population at time 1. We model this financial actuarial world by a probability space omega 2 to the power omega p, where omega, the set of all scenarios in which we are interested, consists of triplets, x1, x2, x3, where x1 is a possible outcome of the stock, x2 is a possible number of survivors in the national population, and x3 is a possible number of survivors in the insured population. Hence, omega is in fact the probability that the vector y1 is takes values in omega is 1. Now we assume that y1 and is are independent under P. What does that mean? It means that the stock market at one hand and survival in the insurance population and in the national population, they are independent. Stock is independent of survival. First question that we have to answer, show that the mean variance hedge now of S, so of the number of survivors in the insurance portfolio, is given by this trading strategy, theta 0S, theta 1S, theta 2 of S. Let us first prove that this is indeed the mean variance hedge for the insurance portfolio liability, and then after that we will give an interpretation to that. Well, the question 1, the mean variance hedge of S follows from this set of equations. We determine theta 1 and theta 2 from these two equations, and then theta 0 follows from this one. Again, we have to calculate a number of variances, covariances, expectations. So we will do that. And then in the end, we find indeed very easily that this is our investment strategy. Our mean variance hedge consists of buying no stocks. This is the number of units of the index that you buy, and this is the number of zero coupon bonds that you buy. If we have a closer look at this solution, we can say the following. There is no investment in the stock, whatever happens. Why is that? It is because of independence. We have assumed that the stock is completely independent of survival. So therefore, an optimal mean variance hedge will not invest in stocks. Let us now look at this term that arises here and that arises here. The covariance between I and S. The covariance between the National Survival Index and the insurance number of survivors. If this covariance increases, so if there is more correlation between the survival in the insurance portfolio and in the national population, then theta 2 of S will increase. So we will invest more in the index and less in the zero coupon bonds. So that means that, to repeat, the higher the correlation between the mortality in the national population and in the insurance portfolio, the more we invest in the survival index and the less we invest in bonds. This is quite intuitive, I would say. Now, let us have a look at a particular case, a theoretical case, which will not be realized in practice, that the covariance between I and S is 0 because, for instance, I and S are independent. So let's say the survival in the insurance portfolio and in the national population, they are in a separate country and the survival is independent. In reality, this will never be the case, but let us have a look at this theoretical case. If this is the case, then we do not only avoid investing in the stock, but we will also not invest in the index because the index is completely independent of the stock. It is completely independent of the survival in the portfolio. And then we would invest everything in zero coupon bonds. Okay. Let us now continue with exercise 14 and take an additional assumption. Let us now assume that GI is II for I is 1 to for all the number of insured people, where uninsured is smaller than N national. So what does this mean? This first condition assumption means, in fact, that the insured population is a subpopulation of the national population. So the national population is Belgium, the insured population is completely within Belgium. And let us assume that all II are independent identically distributed, all people are of the same age and their remaining lifetimes are independent, and the probability of survival is P. Remember, so far we did not assume that survival between the different members of the population were independent. Under these additional assumptions, one can show that the mean variance hedge now reduces to this one. We do not buy zero coupon bonds, we do not buy stocks, but we buy only the national index. And how much do we buy of the national index? If 10% of the population is insured, if 10% of the national population is insured, then we buy 10% of that national index. This seems also intuitive because the insured population is a kind of sample of the national population. So if 10% is insured, you just buy 10% of the index because then you will get 10% of the number of survivors paid. Let us try to prove this. The covariance of IS, we have to calculate this covariance. We write this as the covariance of S plus I minus S and S. And this can be split into parts, the variance of S plus the covariance of I minus S and S. And the covariance of I minus S and S is 0 because I minus S is just the is about the insureds, is about the part of the national population that is not insured. And the not insureds and the insureds are independent by our assumption. So if we work all this out a little bit, we indeed find what we had to find. We do not invest in zero coupon bonds, we do not invest in stocks, and we only buy a proportion of the index, a number of units of the index, and that is a proportion of insured people. If 10% of the people are insured, we buy 10% of this index. Let us now continue with exercise 14 and consider the mean variance hedge-based valuation. So rho of S is the time zero value of the mean variance h of s, plus pi of the hedging error, and pi is assumed to be the standard deviation principle. Show now that our rho of s divided by n insured, or that is the premium to be paid per insured, let's say, is given in this special case by this expression. Well, we get this. Rho of s is by definition the mean variance h of s, its time zero value plus pi of the hedging error. Now we know the mean variance h of s. The mean variance h of s is 0, 0, and then n insured divided by n national. We fill this in, and when we work this out, we find indeed this formula. We find this formula so far. The only thing we still have to calculate is the variance or the standard deviation of the hedging error. In order to calculate this variance, we apply a little bit of a trick. Take your time to have a closer look at it, but in the end you can prove that the variance of this part, the variance of this hedging error, is equal to n national minus n insured times n insured divided by n national multiplied by p multiplied by 1 minus p. If we plug all this information into the formula rho of s, we find indeed that the rho of s is the formula that we had to find. Okay. Now let us give a small interpretation to this formula. This happens on this page here. Rho of s divided by the number of insureds is the premium per insured. If we calculate this, it's y2 divided by n national plus an additional term, which can be rewritten in this form here. Now, rho s divided by n insured, divided by the number of insured, you can easily prove that this is a decreasing function of n insured. If the number of insured increases here, this term here will decrease. The first term does not change with the number of insured. And in the theoretical case that the whole national population is insured, if that is the case, then n insured and n national are equal, and this term even disappears. If n insured is n national, then we find that the rho of s is simply equal to y2. And that's also what we should expect. In this case, s is y2. If the whole population is insured, if the whole national population is insured, but the national population is also traded in the financial market, then the value of rho of s is just the value of the index, and that is y2. This is the end of this video.